Okay, this is the second lecture for tonight. What we're going to look at in the second lecture is the effect that drugs have on synaptic transmission. We talked a little bit about synaptic transmission back in Unit 1 when we talked about how neurons communicate with each other chemically using neurotransmitters. So let's take a look at synaptic transmission and drug use. Okay, so most drugs have effects that reverberate throughout the body. However, psychoactive drugs work primarily by altering neurotransmitter activity in the brain. So it doesn't matter what type of drug we're talking about. If it's a psychoactive drug, it doesn't matter if it's caffeine or cocaine, it doesn't matter if it's alcohol or, heroin. It works by altering neurotransmitter activity in the brain. So let's go into that in a little bit more detail tonight. So neurotransmitters, like we talked about, are chemicals that transmit information between neurons at junctions called synapses. Drugs can affect synaptic transmission by interfering with a variety of processes. So we're going to talk about each of the different processes that can be affected by drugs that are psychoactive. So the first is going to be synthesis. So some drugs can increase or decrease the synthesis of a neurotransmitter, making more or less of it available in the synaptic vesicle for subsequent release. That's the first. Some drugs exert their effects by increasing or decreasing the amount of neurotransmitters released into the synaptic cleft. Surprisingly often, drugs block or slow reuptake, the process in which a neurotransmitter is sponged up from synaptic clefts and recycled by the presynaptic neuron. So some drugs can affect this process called reuptake. Some drugs influence the process in which enzymes in the synaptic cleft metabolize neurotransmitters into inactive forms. And then finally, binding. Some drugs mimic the effects of neurotransmitters by binding to receptor sites and triggering postsynaptic potentials. Others bind to receptors but fail to trigger a postsynaptic potential, thus blocking the action of the normal neurotransmitter by making its receptor site unavailable. Okay. Let's go to the next group of slides. All right, here we go. All right, so let's look at the first class, cocaine and amphetamines, the stimulants. So the action of stimulant drugs like cocaine illustrates how these drugs have selective effects on neurotransmitter activity. Cocaine exerts its effects at norepinephrine and dopamine synapses. Cocaine interferes with the reuptake of norepinephrine and dopamine. As a result, more neurotransmitters are available to bind at receptor sites on the postsynaptic neuron. This causes more postsynaptic potentials than normal. The net result is a storm of increased activity at these synapses. That's where that high comes from. The euphoria associated with cocaine appears to stem from increased activity in the dopamine-releasing neural circuits that originate in the midbrain. Amphetamines, which produce stimulant effects similar to that of cocaine, also affect dopamine and norepinephrine synapses. Amphetamines increase the release of these neurotransmitters by presynaptic neurons, and like cocaine, they slow the process of reuptake. As a result, neurotransmitter molecules pile up, causing increased postsynaptic potentials. The cellular mechanisms underlying the effects of the stimulant drugs also explain why cocaine and amphetamine highs are often followed by an emotional crash that can be marked by feelings of depression and exhaustion. The slowing of the reuptake leaves more neurotransmitter molecules in the affected synapses to stimulate increased activity. However, it also gives the enzymes that metabolize these molecules more opportunity to swoop in and inactivate them, which leaves you with that sort of low, depressed kind of feeling that comes on after the high. So the use of cocaine or methamphetamine can eventually lead to depletion of dopamine and norepinephrine. So the reduced activity at the affected synapses appears to be the cause of the emotional crash experienced by many of the heavy users of these drugs. All right, let's do a quick concept check. In the graph of synaptic transmission, click on the process that cocaine disrupts and norepinephrine and dopamine synapses. So what did we say? Was it reuptake? Correct. In the graph, click on the process besides reuptake that amphetamines affect at norepinephrine and dopamine synapses. What did we say that was? Was it binding? No. Inactivation? No. Release? Yes. In this graph of the emotional effects of cocaine, click on the area that corresponds to the time when the amount of neurotransmitters in the synaptic cleft is greatest. I guess that would be at the high. Of course. Okay, moving on. Let's look at Valium, the opiates, and marijuana. See how they affect synaptic transmission. So the mechanisms that underlie the effects of other psychoactive drugs are not as well understood, but research has yielded some interesting clues. Traditional anti-anxiety drugs or tranquilizers appear to exert their key effects at synapses releasing GABA, a neurotransmitter that triggers inhibitory postsynaptic potentials. Valium and similar drugs bind to dopamine receptor sites within GABA synapses. Once bound, these drugs facilitate the binding of GABA to its receptors. The net result is that these drugs indirectly increase inhibitory activity in the GABA system. This helps keep a lid on neural incitement and anxiety, which makes you sort of feel relaxed and calm when you take these drugs. Heroin and morphine and other opiate drugs bind to special opiate receptor sites where they may help relieve pain by inhibiting the release of something called substance P, a neurotransmitter that carries pain signals to the brain. The euphoric effects of these drugs are thought to be due to a complex interaction between several neurotransmitter systems that result in increased activation in the same dopamine circuits that are thought to account for the reinforcing effects of cocaine. And receptors that are activated by THC, the chemical ingredient in marijuana, sorry, my dog's barking, have been found in the hippocampus and cerebellum. Scientists have also discovered an intentionally produced chemical, Christian anandamide, that affects these receptors. These findings may gradually shed light on how marijuana affects neurotransmitter activity. Okay, and that wraps up this lecture on drugs and their effects on consciousness.